So here we are, yet another webinar situation, right? Where it's a nice online conference, and yeah. So I don't know where you are in the world, but I hope it's a reasonable time of day for you. It's morning for me, so I'm quite happy, and it's snowing like crazy. It's just insane because I would say we had summer-like weather until yesterday, and all of a sudden it's snowing here. Anyways, so much for that. So I'm here to talk about what I call sensible JVM configuration. Now, the talk has been motivated by, I would say, just over the years, just running in all kinds of interesting situations where people have come up with what I call really fun configurations for the JVM. And I guess while I'm talking, I'll just put the obligatory about me slide up so that you can see that. I'm sure you can read that. Anyways, yeah. So really, what we see is that there's a lot of confusion about the JVM configuration and what you should do. And when you get into containerization, the situation just gets completely worse because, you know, I started my career by building real machines, and you could get your hands on them, feel them, you pretty much knew how they worked and everything like that. It's like, yeah, now we're building virtual machines, and you can't really get your hands on them, and there's all kinds of weird things going on there, and it's not clear to many people, you know, what's actually happening here. And to make matters worse, and you've got these, you know, real hardware supporting it, you got these container things happening, and then you end up with this Java virtual machine in there, and you have like configuration on top of configuration on top of configuration, and it's just not surprising that people are a bit confused about the situation, especially when you get into the JVM. The JVM contains more than 700 flags. Right. And, you know, you can go to OpenJDK, it's all the source codes in GitHub, you can download it or check it out. And you can find all these flags in these global.hpp files. There's about 16 of them currently. And, you know, these flags are all categorized and stuff like that. So depending on how you build the JVM, you're going to have different groups of flags available to you. Yeah, and you can see how this gets really, really confusing quite quickly, as you know. So being part of Microsoft, in the Java group, we talked to the .NET guys, and you know, they're utterly amazed at how configurable the JVM is. Sort of a bit envious in many cases, but you know, it does become confusing. Now you might say, okay, well, how can I look at the current values that I'm using? Well, you know, you can use this print flags final. They're showed up in MX beans, which means that you can use tools to attach, which will inspect and get these values for you, so that you can print them all out. You know, and that will give you an idea of like what your runtime values are. And here you can see that I've just took the top of the list, so I didn't want to list all 700, but you know, you get an idea about what's going on here. And you can see they all come, in this case, these are all product flags, and they're all set at the you know, default values. And the funny thing about like having all these configurations is that when you get down to it, there's not really anyone that understands what combinations of these, you know, what effect combinations of these flags would have on your runtime. So you get into situations where even people building the JVM expect certain behaviors, but because of interactions between other flags, and you know, it suddenly gets confusing to understand how the JVM is going to behave in certain situations, or in basically any situation. You know, so the quick question is like, you know, that most people have is like, which flags I'm going to use, when I'm going to use them, and how am I going to use them? And this is you know, the real question. And really, you know, if you don't want to stay for the entire talk and see what some of the more detailed answers are, you know, we'll give you the spoiler alert right now. If you don't want the spoiler alert until later, then you can just switch your audio off for a second, and video, don't look at the video. And you know, sensible JVM configuration is really to start with default values. These default values come because the JVM engineers in our group at Oracle, at Bellsoft, at Azul, all of these places that are producing a JVM, they're running benchmarks. And they're running these benchmarks, and they're using these benchmarks to help determine what these default values should be, right? Because a lot of them are based on, current state of hardware, all kinds of different things. All right, so starting with the default values generally give you the best results, but there are some places where you're going to want to give the JVM a hint, because there's something unique to what you're doing, and because of that, the JVM, may need to be configured. But in this case, you're going to have to make some measurements, right? And the measurements are going to hopefully point to some issue. And when you go through the flags, you're going to say, okay, these are the sets of flags that seem to address that particular issue. Now, the notable exception to, the things that you might want to use, or sorry, the things that you might always want to configure away from defaults are garbage collection and, in general, memory settings. And we'll explore more of this as we go through the presentation, right? Now, so I wanted to start this week with, one of the things that we typically see, just to back this up with the real world. So this is not the worst one I could find, but, I thought it was pretty much good enough. But you can see here's a whole bunch of, block of text at you. If you can't read it, yeah, don't be worried. No one else can either. I certainly can't. So in this case, what I did is I just sort of broke it out here so it makes it a little easier to understand what's going on. So here we are, 25 flags set, 2 properties. And it's really funny, when you start looking at which flags are being set, you can sort of see the underlying problems that, that the people were trying to solve by using flags. So, first let's go through the fun ones here. This is duplicated. Not only is it duplicated, it's actually in the version of the JVM that they're using, it was deprecated. And there was also another flag that was in there that was deprecated. So this is why we call it tuning by Folklore. It's because, somebody inherited a whole bunch of flags, they had an issue, they were looking at it, so they added more flags to the mass, and then, it just grows over time. And of course, we're afraid to take away the old flags because we don't know what they're doing, why they were set, what problem they were trying to solve, so basically let's not touch them, right? And that's the attitude generally. And to be honest, it's fair enough. I mean, when you get into these situations, this is you're touching things which you don't really want to in many cases. But in these cases, we can safely get rid of them because I know they're duplicated and deprecated. And then we get this funny thing here. We have conflicting flags, right? So we have disable explicit GC, and then we have explicit GC invokes concurrent. And you're going like, okay, wait a second. So what are we doing? Are we disabling it, or are we invoking a concurrent? And, this is one of those confusing situations where I can honestly tell you, I don't even know what's going to happen. In this case, I didn't try it out myself, or I didn't look at the source code to explore this one. All I know is that when I combine it with those 2 flags, it looks like they have this issue where somebody's calling system GC and they're aggressively trying to, get rid of that call by flag setting. Now, you actually can do that. But of course, it's always better to go into the source code, figure out where the source of that call is, and eliminate it that way. Moreover, if we look at it, these 2 are actually set to the default value, right? So these are actually all set at defaults. And as a matter of fact, if you go through the whole list here, you're going to see that they're not the only ones set at the default value. We have all these other flags that are actually set at the default value, meaning that we don't actually need them either. So we can just eliminate them. Here's a bunch of settings. I don't want to get in too deeply to it, but there's all kinds of problems when you're trying to do this particular type of configuration. The less egregious one is setting the min heap size to the max heap size. That's like the top 2 there. But the other ones, you sort of really have to know what you're doing and understand what's going on in order to be able to apply them. And it's, given everything else in here, it's unlikely that was the case here. This sort of looks like, again, going out to Stack Overflow or something and getting some things and trying them out. Now, I suspect here they were probably getting a lot of full GCs because of what's known as heap fragmentation. And so that's what they were trying to fight. Just by the combination of flags that are here. Okay, so now we get into other flags that I would say really don't have any supporting evidence, and I don't really have anything to say about the other ones except for, so if we look at, the reduction that we've gone through and everything like that, we've essentially reduced our command line to something that looked like the top to something that looks like the bottom, which of course is much more manageable. Right. And in this case, we make the change and there's really no loss. There's no loss in making this change. Okay. But you can see the problem, right? I'm in a environment where there's, a lot of moving parts, a lot of things are happening, and, and I'm just trying to make the best of the situation. And we end up with something like this. Okay. So, more of the spoiler alert, it's like, how do we actually configure this? An approach is like, start with defaults, let ergonomics do its thing. So in other words, the ergonomics is going to try to calculate defaults for you, right? Measure the application behavior and change things one by one. So generally we try to get the memory issues out of the way first. Then we might look at threading issues. And then once we've dealt with all of those things, then I might make changes to other settings once I understand what's going on. But, honestly, by the time you set the garbage collector and the Java heap size, generally, there's not much else that you need to touch, to make things work. So if you're using defaults, it helps know what they are and how they get set, right? So let's go through a little bit of that. So we say, first, I mentioned this term ergonomics. So here from Oracle docs, they're defining what ergonomics is. It's the process by which Java Virtual Machine and garbage collection heuristics, such as behavior-based heuristics, improve application performance. Now we can, niggle over the details of this. I actually had a conversation with a colleague yesterday about this definition. He was not, he didn't like it that much. I don't think it's that bad, but let's see what they mean here with this whole thing, right? So we have a JVM, we're going to start it up. It's going to probe into the hardware. It's going to figure out, okay, how much memory do we have? How much CPU do we have? And then it's going to use those values to calculate internal cache sizes, which should include Java heap, code cache, metaspace, compressed code, just a whole bunch of different caches that are in the JVM. It's going to calculate which garbage collector should be using. So that's going to tell you how to structure Java heap, number of helper threads for the garbage collector, for the hotspot compiler. Of course, fork join pool is going to be set to the number of of the number of cores that you have on the hardware. So there's a whole bunch of different calculations that are done to actually help understand. One of the more important calculations that happens is that as the application is running, there's going to be data that ergonomics is going to be collecting, and it's going to make adjustments to the runtime based on these ergonomics it's going to collect. Like, so the most infamous one is I'm going to resize the Java heap. And I want to resize the Java heap because I want to minimize GC pause times, but I also want to minimize GC overhead. So at that point, what we're doing is we're doing a balancing act between too small, we call it too frequently, too large. All of a sudden we can have large overheads when we do process, right? So large tail latency events. So if we can basically have it adjust according to current workloads, then we can, we don't have to stick to one size. We can just have it adapt to, the current load, and hopefully, allow us to minimize both the impact of the garbage collection and to minimize the impact of the garbage collector on the runtime and memory management in general. Right, so as I mentioned before, there's everything that it's going to adjust and more. Settings affected, these settings are going to be affected by the class of machine that you're on. Now, the class of machine was unfortunately defined in 1995, which means my phone actually qualifies as a server class piece of machine as far as the JVM is concerned, which is odd, but you know, that's what it is. And you can go through the JVM code and you can basically see, we're going to ask are we on a server class machine? And if we are, then we're going to use G1GC as our default garbage collector. And if not, so if we're in a client class machine, then we're going to use the serial collector, right, as our default collector. So that's one of the first distinctions it's going to make between client and server. Now you might say, okay, so what does it mean to be server class or client class machine? Well, here's actually the code that goes through it. And effectively, what you're going to see if you do the calculations, there is I've added a comment there, it's like 1792 gigabytes of memory. So we need more than that amount of memory, which is basically 2 gigs minus a fraction that they consider loss for buffers and things like that. And like 1/8, I guess. And we also have to have, you can say, highlighted logical processors, right? So we need to have more than one core, right? So when we have multiple cores and, approximately 2 gigs of memory, then we're going to be considered to be a server class machine. Now you can see why my phone is a server class machine, right? So, and yours is too, by that standard. Okay. So, so more ergonomics, you can read the whole thing. So we calculate GC helper threads. So if you have less than 5 cores, then helper threads is equal to the number of cores. The JIT compiler has a slightly different calculation. But you can see what we're doing is by probing into the hardware, we can just take those values and plug them into these formulas. And we can get into a situation where we can run concurrently with our application and hopefully not impact throughput of the application that much by taking away CPU. And we can also run, in a full stop the world mode and get things done very quickly so that our pause times are reduced. Now, in terms of memory, you can see the ergonomics are basically 1/64 of real memory as our initial heap size, but it will jump to either 1/4 or 1/2 of real memory, depending upon the amount of memory that you actually have. Now, you might notice that all of this here has to do with real memory and real numbers of cores, right? And, we generally deploying containers today. So, the next question really is, how does that all work? Now, here we can look at the GC underscore globals.hpp. So that's like a general file that's configurations for everybody. And you can see how how these macros are defined. So we have min heap fraction, max heap fraction, initial RAM fraction, max RAM percentage, and so you can see all the flags here, and you can see where the where these values actually come from, and they come from these particular ratios and percentages. Depends on the flags that you're using. Okay, right. So now let's inject a container into it, and this is the way it was, prior to. So same situation, JVM starts up, goes down to the hardware, figures out how much memory, how many cores, does all the same calculations, so on and so forth. And we end up with a situation where, all of a sudden I'm just sizing based on the hardware and not really on the constraints that I've given the container, which causes a whole bunch of different issues. Right. So if you get into a situation where you have a very small container, then of course, as soon as you try to allocate memory for the JVM to run inside the container, then you're going to get a container out of memory error, and it's going to kill the container, and not a very desirable, start. And again, we're going to use the core counts, the host core counts for calculating the thread pool, which means that if we start launching many of these, all of a sudden we're going to have a ton of competition for the CPU, and that's going to give us one form of noisy neighbors, right? You know, the idea being that if the garbage collector runs, I don't really want anything competing with it, because that means my application is paused. And if it's paused, it means, you know, incoming requests are all stacking up, and that's like a big tail latency event. What will happen is then, of course, you'll have those effects because somebody else is interfering with your garbage collector's ability to run, just because of, you know, how all the scheduling works and things like that. So when we get into 1.8 U31, 131, then we start getting in a situation where we start making the Java virtual machine container aware, so that it goes down to the container configurations and gets that information, and then it calculates everything based off of that. So that gets into a slightly better situation. But then you have to ask, the question is, right, how do people tend to deploy? And the containers that they tend to deploy in are 1 gigabyte, 1 core. And since they're 1 gigabyte, 1 core, and you go back to the ergonomic calculation, you can see like, oh, okay, so we're no longer in a server machine, we're in a client machine. And the client machines run differently than the server machines. They're configured differently, and they don't optimize as aggressively. So there's all kinds of different performance choices that are made, because, you know, client was intended to be short running. In other words, focus on getting it up, started running. We don't care about peak performance, right? Where server is, we don't, you know, we want to get to peak performance, which means that we're willing to take a little longer startup cost in order to get to peak performance. So you can see the concerns are different in both implementations, right? The other thing is, like, if you look at how people deploy in this consider that, then they end up actually spending a lot more money than they should, simply because of the overhead of running all of these containers and the number of containers that they need, because they have suboptimal performance from the containers that they have, you know, from the applications they've deployed in these undersized containers. You know, and we know one of the primary drivers of costs in the cloud is going to be memory. You know, memory really is going to dictate a lot of the, you know, how you're going to configure things, and of course that's going to dictate the hardware that you need to lease, and, you know, and that's, since you're going to have to lease more hardware in this case, you end up spending more money, right? So, and the other thing you have to know is, like, the memory that you're giving your JVM may not be the amount of memory that your application actually needs, right? Too small increases the tail latency picture in your application. So you're just going to have higher effects on P99 from basically what I call like internal effects, all right? And if you make them too big in this case, you're wasting money, because you're just spending money on memory that you don't actually need, right? And this can actually have an overall effect on application latency as well as tail latency. So I want to distinguish here between tail latencies and application latency. So application latency is going to be like your typical like latency picture. And the tail latency is, of course, going to be the end, like, you know, what does it look at the extremes, you know, 99.9th percentile and things like that, or things start to tail off. So you see, as you reduce the amount of memory, what happens is that your tail latency is going to push down into your application latency, and you're going to end up with overall worse performance. And it costs you more to run that also. Takeaway: you need to right-size the JVM to meet your application needs, then configure the container to support this. And I'm not sure that this is common practice from the data that we're getting from the industry. Okay. So if you look at how we deal with memory, I don't want to go into a garbage collection talk here because that's something onto its own, but you can see that I just have this chart here that basically maps out the different memory pools in Java Heap and gives you a little bit of a roadmap as to what the flags are and some of the values are for this, as well as a bit of the terminology here. Young generation, Eden is for initial allocation, and survivors are there to retain short-lived data, which we also call transient data. Tenured is to retain long-lived data. So you can see that each of the spaces play a different role, and because they play a different role, we need to apply a different tuning strategy to them all. The tuning strategy for Eden is to use the size to control frequency, because think of it like a bucket, and we're going to pour water into it, and when it's full, we need to empty it, right? So there's two levers we have here. How big is the bucket, and how fast are we pouring, right? So that's what we want to do. Since the application is controlling the pour rate we'll leave it at that. The Eden size is really the size of your bucket. All right, and the survivor is to basically there to hold on to spillage, right, until we get it, to delay things going up into tenured, where we actually want to store it for longer term. We were going to maintain it there for the long term, and in this case, since that has a different role, we're going to say, well, okay, how big is the live data set size? And generally, we're going to want to make that space twice as big to give us a little bit of working room. If you get to bigger space, that generally means that you're pushing transient data up into tenured space, which means you need to go back to your young generational space to make that bigger. Right, okay. So this is for generational spaces. The details for each of the collectors is going to be slightly different, but that's the general idea. Okay, so really in this case, what we want to do is figure out, okay, how big we need to make these spaces to accommodate our application behavior, and then really try to let ergonomics do the rest. So here's an example. So we have an average allocation rate here of, say 200 megabytes per second. It's 189 in this particular chart. And then when I look at here, I'm just trying to get an estimate of the live data set size, and I'm going to just arbitrarily say it's 1.5 gigs. Now, you might notice that there's a big spread between that green line and the top of the data here. And that's really because there's a lot of transient data being pushed up in this application. In fact, I would say that 85% of the time, the data from young gen is being pushed into the space when it really shouldn't be. Well, each collection is pushing data up here. So that's really a bad situation. We want to try to clean that up, because that just hyperactivates the garbage collector, and it impacts your tail latencies, right? So in this case, I'm going to use the 89 megas. So I'm going to say if I want a collection every 10 seconds approximately, that's what I can tolerate. Then so 189 times 10 equals 2 gigs. So you can see our math is really sloppy here, and it doesn't have to be precise. But and we actually don't want it to be. So we're going to make the survivor space the same size as the Eden space. We're going to go tenured at 1.5 gigs times 3. In this case, I'll just give it a little extra working room till we get things sorted, and then maybe on the next round I'll draw it in to make it shorter. We'll do the math. Actually, I did the math mistakenly with the factor of 2. So it's a bit of a bug here. I'll just actually change that to a 2 and a 2. So the correction shows up on the video. Okay. Anyways, the point is that now you can see how much heap I need, and then there's my command line parameters for configuring heap. Yeah, we're done, right? Okay. Now let's add in the container dynamics here, right? So the question is how big a container do we need to support all this? Well, again, we have to figure out, okay, what are all the parts, and what are the size of all the parts, and then add it all together, and then we can figure out, what it is that we need. So the JVM has a fixed and variable size segment. So the fixed size is basically the code, for the JVM, which is like the shared text and dynamically and statically loaded text space in the process. And then it has some variable areas, which I would call Java heap as being a variable here, area, code cache, and if you have third-party libraries that are involved here, that like Cassandra does like off-heap storage, so it maps things in. So you have to sort of add up all these parts to figure, okay, what's the fixed size of this whole thing? We've configured Java heap, so we have with that an idea of like what the variable size of the whole thing is. So like add it all together, and when we do that, and we're going to add a little extra for system stuff, at that point you can see that we can use that to actually now accurately calculate how big the container needs to be, right? So we can just do that. So one of the things that the JVM supports, one of the parameters is what's known as like MaxRAMPercentage, right? So what that means is that when the JVM starts, it's setting the Java heap to be 50% in this case, the way I have it set, of the of the available memory. So it's going to go down into the container, how much memory been allocated, 1 gig, no problem. Java heap is now going to be 500 megabytes. And so then the question becomes, how does this dynamic work, right? If we do that, because this is one of the most common things that people do. They'll just set this max RAM percentage if they set anything at all. And the fun thing is that when you get into a situation like this, so here's the original container, we set it up and everything is good, so it fits quite nicely. There's really no waste. Now we go and expand the container. Now, if we use the flag here -xmx, so we fix the Java heap size so that it basically overrides ergonomics, so we don't get the dynamic sizing in this case, but it's just fixed. You can see expanding the container really doesn't do anything because the JVM remains the same size. So we end up with all this wasted memory in the container that's just there, right? Now, if you use the other parameter here, which is the MaxRAMPercentage, you can see that the JVM is going to grow to fit into the container. However, you can see what's happening is that as we make the container bigger and bigger, the JVM will get bigger, but the waste is going to get bigger. So in this case, I'd always recommend that you use the -xmx to set the max heap size and not use the percentages, because that is going to allow you to be aggressive to consume all the containers. Sorry. So I think one of the things I missed at the beginning is saying is like, if you look at garbage collection, it's like, why did they change those values? Well, they wanted multiple JVMs to run on the same hardware and cooperate with each other, right? So they were favoring cooperation. But when you get into a container environment, what you want is the JVM to be greedy and take all the memory that's available to it. And, so just, so it's a complete change in philosophy. So these parameters sort of reflect that philosophy of sharing and not being greedy. And so, this then leads to this waste because you're not going to likely run 2 JVMs within the same container. Right. Now, so that's the memory issue. And I don't have any questions yet, except for we do have people around here that's asking some questions. Okay. What do we do? How are we doing for time? Okay, not so bad. Controlling costs. Thread to core counts are another thing that we need to consider, right? So because this is going to impact latencies also. Too few threads are going to increase application latency, and too few cores are also going to increase application latency. And this is because if I have too few threads, that means I'm not going to be able to saturate the cores. And your goal should be to saturate the cores, unlike what most people think, right? Now, of course, I might want headroom for whatever, but if I need that, then generally with today's architectures, I should be able to scale out to accommodate that. Right, so too few threads means I can't saturate the cores when I need to. Too few cores means I'm just going to be competing for the cores that are there, which means threads are going to be stalled, waiting to be scheduled for cores. Of course, too many cores means your machine is bigger than you need it to be, your virtual one, all right? And and too many threads also was going to have the effect of adding to the application tail latencies, because the thread counts actually have an effect on one portion of the garbage collection process. So that'll increase your pause times. So let's take a look at some situations here. So say we have like a 64 core machine, and in this situation, you can find, if you do the calculations, the JVM is going to get approximately 40 GC helper threads, right? So that's pretty good. So we don't mind that. That means the garbage collection process should happen pretty quick. Now, the question is, like, what happens if we launch 10 instances of this JVM on that particular piece of hardware? In this case, we're going to have the JVM getting 400 GC helper threads. Now that gets into a conversation of, with all the other threads running on the machine, like what's happening here. So, with sizing of the question is like, am I doing synchronous work, or am I doing async work? So with synchronous work, that means my threads are likely going to be blocked doing something, or while waiting for stuff for a while. When the async world, I'm going to throw up either a future or a promise, and then I'm going to go off and do other things. And, when the future is completed or the promise has been completed, then I'll go back to that particular task. But the point is, now in the async world, the threads, fewer threads are going to be a lot busier than the sync world, where you're going to have lots of threads being not so busy. And of course, that really complicates the picture as to how well is this 64 core machine going to support what's going on. And unfortunately, I don't really have any good answers to that, except for the more asynchronous, the fewer threads that you definitely want. Now, the GC work, I would consider to be one of these things that when it runs, you actually want it to run now, because that's having a direct impact on the tail latencies of your application. And if you have 400 threads and you have a couple of JVMs all of a sudden decide to do garbage collection at the same time, we can actually calculate the probability of this happening fairly easily. It's non-zero, and it's not even close to zero with this number of JVMs. What happens is that, one machine's garbage collector is going to be interfering with another machine, another virtual machine's garbage collector running, and all of a sudden you get much longer pauses and much longer tail latencies under this situation, right? So you need to be careful about how you stack things up on a machine. Now you can limit things by using this particular flag, right? And if not all threads are active, this is likely going to offer some relief. But if you limit the number of processors for each machine, then of course you get fewer helper threads, which means that you're going to have potentially longer garbage collection pause times. So let's take a look at this particular case study. This came to us maybe say about 2 months ago. So Kubernetes deployed application thread counts. So we had a neti thread pool in there. There's about 50 threads in there. JDBC connection pool is about 50 threads in there. The fork join pool was configured to have 20 threads. I don't know why they configured that, but they did. GC helper threads 4, JIT compiler threads 2, and so on and so forth. And you end up with a total thread count of 154 threads. Now, the kicker is they went and decided to deploy this in Kubernetes. So then, of course, in Kubernetes configuration, you have to tell the container how many milli-cores that it has, right? So each container is configured with, a number of slices of the core, and that quota is going to be refreshed every 100 milliseconds. So these things are both configurable, the refresh period and the number of slices that you get. So typically what you do is you slice the core up into 1,000 slices, called a milli-core, and so to get the full core, you need to give the container 1,000 of these things. So 1,000 milli-cores every 100 milliseconds. At issue is multiple threads in the container all working at the same time are just going to destroy that 1,000 milli-core budget very, very quickly, in far less time than 100 milliseconds. And when that happens, you end up with the situation where you just end up with, you're just core starved, right? Because you're just going to go blasting for, I don't know, 10 milliseconds. And now you're basically swapped out for 90 milliseconds waiting for your quota to be topped up again. And of course, that's a different, difficult situation, right? So now we have, like in this case, 154 threads deployed with 1.578 millicores. Do not ask me why 1.578. I'm not making that up. It's a real number, all right? And we talked to the .NET CLR engineers, and they're saying, like, what do we do with fractional cores? Because, all our heuristics are designed for whole number cores. So that's another issue too, I guess. The JVM will actually round this up to 2 and then make its calculations based on 2. However, you can see that, there's not 2 here. So we're already multi-threaded. In this case, we're like really multi-threaded in the sense that we have 154 threads running for this thing on effectively 1.5 cores, right? So you can understand the situation here that we're just going to be core starved in this particular application. Right. Right. The typical reactions, unfortunately, this comes into a deployment, how do you manage this in the real world, I guess, right? Typical reactions is they're going to increase the heap size, and that's really going to increase your cost of goods sold. That's what COGS means in this case, right? In other words, you're spending more dollars to run your application. Increase the number of replicates. Again, you're spending more dollars to run your application. Or in severe cases, people will just simply move to another tech stack. And we've actually talked one group out of doing that, they didn't quite understand what was going on. We're able to help them. They were running in the red, and they figured, okay, well, we're just going to move this whole thing to lift shift, right? Which would have been in this case, like a multi-year effort, and it's not sure they would have brought their community along with them in the tech stack shift. So there was huge costs in making that particular decision. In this case, what we were able to do is we were able to get them to scale down, not scale up, but in this case, scale down and then scale out. And in that particular case, that solved the problem. And it worked in that particular case because their bottleneck was actually in the host operating system. In other words, the way the applications were working, that's where the pressure point was in the whole thing. So in that particular case, the scale down, scale out was the best option. And this really gets to the point you have to know where your bottleneck is, because if your bottleneck is in other places, like for instance in some of the in the JVM or in the application stack itself, then in many of those cases we found the best option was to scale up and then scale out, and that was a good way of reducing costs. So really having a good handle on where the current choke point is in your application really is helpful in deciding whether you should scale down or scale up. In most cases, we find that for Java, scaling up is much better. Certainly running with 2,000 millicores is much, much, much better than running with 1,000 millicores. It gives much better results and actually allows you to reduce costs when you get when you start running with that type of configuration. Right. So, and again, really understanding bottlenecks help you now to decide, okay, is it best to scale up, scale down? And then once you've got the JVM and your application right-sized in a single node, then you can look at it and say, okay, now I can scale out. And that's really the technique that we would like to use here. So, you know, getting back to our approach here, we can see that, you know, again, start with defaults. Ergonomics does work quite well in many cases. Memory and garbage collector are the things that we might want to change. And there's, you know, plenty of material out there to work in, you know, how to know when to use which garbage collector. People would say serial garbage collector. That's horrible. In my estimation, it's actually not. It's a very efficient garbage collector. It is single threaded, but for small heaps, it works very, very well, much better than the collectors that are designed to scale up, like G1, right? You know, so up to a certain size, then the serial collector actually is much better, and that size is actually bigger than what ergonomics will, you know, will tell you, right? And again, you can see that we went through the memory configuration, so that's something that you probably want to go through, so you can get some data, GC logs, or telemetry from the JVM itself will help you with that. And then sort out number of threads, make sure your threading is adequate. What we're seeing is high pressure on the thread scheduler. I didn't put anything in here on how thread scheduling works, but effectively you end up having your core starve for work, because not because there's not work to do, but simply because the thread schedulers can't keep up with what's going on. And in those cases, you know, again, a scale down, scale out is probably a better option for you, right? Right. And any other settings once memory is out of the way, and you're going to find that setting anything else is really a rare condition. It's very rare that we'll go into a site and say, oh yeah, we need to now figure out how the, you know, how to adjust how the JIT compiler is working in these particular cases. I mean, it happens, but I would say it's a very rare situation. And I'd also say that if you get to that level, unless you have JVM expertise in there, it's probably best to go out and find some help for that particular task. Okay. And really, that's all I have to say. Well, I could say more, I guess, but you know, that's all I'll say for now. If you're tweet.
Thank you very much.
Me.
I was looking to the chat, but we don't have any question at the moment.
Okay.
If anyone wants to ask now, maybe. If not, we are moving to the main track.
Okay.
Thanks again for joining Peak IT.